So today the agenda is about spectrum, and my talk is going to sort of give an overview of what the day will be like, try to set the stage for why, how we got to where we are, and to sort of start, I would just want to make a quick announcement about a slight change in the agenda. So we have Darpa coming to introduce the Darpa Spectrum Challenge, and there is a demo that will be run from here, and the original plan had been to immediately do the demo right at the end of the Darpa talk, but we have a break in between, and we need the break to actually set up the demo. So the actual demonstration will be done immediately following the break, all right, after the Darpa talk. All right, so the title of my talk is Big Bandwidth, and you'll understand what I mean by big bandwidth. It's also a play on the hot topic of big data. So I want to set the stage by telling you how we got to where we are. All right, and basically it's a story of the spectrum debate. We had two conflicting sort of viewpoints on how to deal with spectrum. One was this notion of open access, just let anyone use spectrum. And examples of this range from technology success stories like 802.11, all right, and how if anyone could access spectrum, you could more rapidly deploy technology. On the other hand, there was a lot of work in the economic field about how to actually buy, trade, sell spectrum rights. And the idea would be then that you would build a marketplace. I would own some spectrum, I'd sell it to you, and so on. And again, there was a lot of economic work done both by economists and also by wireless researchers in this area. And these two conflicting sides went along their separate paths, and they didn't necessarily agree with each other on the various approaches to dealing with issues like tragedy of the commons and so on. But what everyone did agree with is the last bullet, which is that currently the spectrum use is inefficient, and the approach that the FCC has had has led to this sort of false sense of spectrum scarcity. So I now put up this picture of how our spectrum is allocated, and frankly, spectrum allocation is quite complex. This is, different colors represent assignments to different bands, different purposes. All right. There's no real rationale for how this is, being done or was done, and a lot of it is legacy. And the consequence of this is that spectrum utilization has been quite poor. All right. And so here is a depiction of spectrum in 3 different areas: Atlanta, New Orleans, and San Diego. You can see, same band, quite different profiles. And on the right-hand side is just a snapshot of spectrum usage versus frequency. And you'll see that there's a lot of open holes. All right. Even though these bands have been allocated, they're not being used. All right. So the spectrum debate emerged, and it was driven largely by research themes. All right, and a couple of the research themes that came out of the work of the past decade was this notion that hierarchical networks were more efficient. If we cooperate, everyone sort of wins, so we can improve our achievable communication rates if we sort of cooperate and coordinate our communications. But to have cooperation, we need this notion of global awareness. We coordinate with each other. How do you do that? There was also then this idea that radios must then communicate with each other. So how do you have efficient communication? They have to discover spectrum opportunities. All right. And in the end, out of this past decade of work has been a lot of progression towards this notion of dynamic spectrum access. All right. Short-term property rights. I would lease the use of a band of spectrum from you for a short period of time. And in particular, we've also had platforms advance, such as cognitive radio platforms. All right. So where are we? In 2011, State of the Union address, President Obama announced the National Broadband Initiative, and basically it's going to open up lots and lots of spectrum. All right, so the FCC opened up a whole bunch of spectrum in the 300 to 400 megahertz band, and also the National Broadband Plan promised to open up about 500 megahertz in the next 10 years. With all this bandwidth, with cognitive radios, with issues of coexistence, economic factors, maybe we can build marketplaces and so on. There's a lot of unsolved problems that need to be tackled. And so, today, what are you going to hear about? Well, today's agenda is going to try to cover different aspects of what we're calling big bandwidth and its issues. So there's large spectrum chunks that are severely underutilized. These spectrum opportunities, they have to be found. All right, and there will be some discussion about scanning spectrum today. And one of the problems with scanning spectrum is there's a lot of it, and you've got to find that needle in this big haystack. There are opportunities and there are risks with these opportunities. All right, how do we make and disseminate these risks? All right, and information about these risks and these opportunities. So there'll be a talk today also about sort of a spectrum server that will tell and share information about here's an opportunity, here's the possible interference in that area, and so on. Another problem is how do users lease rights to spectrum? All right, how do you trade? If I own the rights to a spectrum and I want to sell it to this guy, you would like an assurance that I'm releasing those rights to you, and that there's a guarantee that you can then use it. So we're going to also have a talk on how to trade spectrum rights, spectrum usage. Another problem is then the abuse of spectrum. It's quite likely to happen. Cognitive radio platforms are highly programmable, so what's to stop me from programming it to do whatever I want? Since there is so much bandwidth, issue number 5, right, it's now allows for the possibility for us to use this wide bandwidth itself as a very wideband communication channel, or to also just address issues of stacking different communications on top of each other in that wide bandwidth. And one of the problems is, how do we then efficiently model these channels, these very wide 100, 200 megahertz channels, all right, efficiently? And we're going to have a talk today about how to perform simulations and emulations efficiently for 200 megahertz channels, if you will, with a complexity that's significantly reduced, yet captures the important statistical phenomena of those wide channels. We also have an invited talk today about coexistence between radar and commercial wireless systems. In particular, a lot of our radar systems interfere with wireless technologies in other countries, and there's an issue there about coordinating and allowing them to coexist. And then generally, how do we find the best radio strategies to use spectrum cooperatively and competitively? And that is also a segue into the Darpa Spectrum Challenge. So that was the overview, and now just to give you quick appetizers. So there will be a talk later on today about the idea of a network service that supports dynamic spectrum access, notifying people, here are the opportunities and here are the risks. So look forward to that talk this afternoon. As I mentioned, you want to be able to efficiently simulate these wide bandwidth channels. There's going to be a talk by Shweta. Shweta is also in the afternoon, on ways to reduce the complexity in studying multi-party communications in wide bandwidth channels. All right. We have an invited talk today from ACS, Applied Communications Sciences. And they're going to talk about an architecture that supports tasking of radios so that they can I would say, cooperatively achieve mapping of spectrum or dealing with spectrum tasks. All right, and so this is just an overview of the talk that will be given there. There's a lot of issues when you have a distributed system about performance and assigning tasks and yet not interfering with primary functions. We also have a talk this morning by Ivan Seskar about what I'm calling a new cognitive radio platform. He didn't want me to use the word new, but basically it's a software radio platform that we have here at WINLAB, and it's sort of a new architecture for it. And so he'll talk about that, and that's what we call the WISER platform. And then the last set of slides here talks about my own work in spectrum scanning, and the problem is if you want to detect anomalous activity, you really need to understand the implications of your radio, your cognitive radio, your scanning radio, in terms of its ability to scan a certain amount of bandwidth, its ability to tune to the next frequency and scan, how long it takes, issues of dwell time, transition, and so on. All right, and in particular, if you're looking for an anomalous event, all right, you need to understand then the conflicting strategies that you have as a scanner in terms of the amount of bandwidth you scan and the amount of duration that you dwell on that bandwidth versus the strategy that an opponent might have in terms of the amount of bandwidth they use versus the amount of time they try to sneak. All right, and these are, again, sort of conflicting issues. All right, in this bottom left picture here, an invader tries to use a very wide band, all right, but for a very short time, wide band allowing them to communicate a lot per unit of time, but a sliding scanning strategy will be guaranteed to eventually catch him. All right, on the other hand, there is a probability of detection for a different strategy where he uses less bandwidth but for a longer duration of time, and a sliding strategy might miss him. So studying those type of issues. And we have a project that we're starting on this. And then on the right-hand side is the segue into another invited talk that we have today from the University of Georgia. We have someone who's going to talk about using microwave photonics for scanning very large amounts of bandwidth. This is a very different type of thing than we normally have here at WINLAB. It's where sort of the wireless world interfaces with the optical world. And so we have what I think is going to be a very interesting talk on how one can use photonic techniques to scan large amounts of bandwidth. And then finally wrap up with when you are trying to do anomaly detection in spectrum, you need to understand your strategy for performing detection, and in particular, if you want to do a distributed detection strategy, you should somehow take into account the propagation characteristics of the environment. All right, and this is some results on the right-hand side of probability of detection versus false alarm for a approach that we devised where basically what we're doing is looking for an anomalous transmitter and how it alters your perception of the propagation characteristics for the environment. All right, and so with that, I will wrap up and have Janne hand off to and introduce the next speaker.